Let us talk about analysis of binary search. Let's first do a quick recap of the binary search. In binary search algorithm, we are given a sorted array and an element to be searched. We search this element by first going to the mid. We first go to the mid, compare mid element with the x, and if they are same, we return mid. If array mid is greater than x, then we go to the left side of this array. To go to the left side, we change high equal to mid minus 1 and we repeat. And if mid element is smaller than x, then we go to the right of x, right side of this array. And when we go to the right side, we change our low to mid plus 1. This is what we do in binary search. Now, how much time this binary search process takes? Here we have drawn a tree for all execution paths for all possible successful searches. So what do we mean by successful search? A search is called successful when the element you are searching in the array is present. If the element that you are searching in the array is not present, we call it an unsuccessful search. We will first analyze time complexity for successful searches, then we will talk about unsuccessful searches. So here we have a tree. It's not a recursion tree. It shows all possible execution paths for the successful searches. Let's understand this tree with different possible execution paths. What we do binary search, in this sorted array, we first compute the mid, and mid is 0 plus 14 by 2 because high is 15 and low is 0, which is 7. So first thing we do is we compare A7 with X, and if A7 and X are same, then we stop our binary search at this point only, right? So this is one possible end of binary search, and in this possible end, we did only one iteration of the loop, right? We did write a code where we were running a loop. Now when this A7 is greater than X, what we do is we go to the left side. When we go to the left side, we change our high to mid minus 1. So our now high becomes 6. And we now compute the mid as 0 plus 6 by 2, which turns out to be 3. That's why we are comparing X with A3. So when we compare X with A3, again there's a possibility that X and A3 are same. And we stop here because X and A3 are same and we found the element. So when X is equal to A3, how many iterations we did? We did 2 iterations of the loop, right? So this case requires 2 iterations of the loop that we wrote in the binary search code. Now again, if X is smaller than A3, we go to this side. We have high is equal to 2 now, and mid is going to be 0 plus 2 by 2, which is going to be 1. So that's why we compare with A1. Now if X is equal to A1, we stop at this point and we do 3 iterations of this loop when we have X equal to A1. Again, we follow the same process for A0, A2 and all the other elements in this tree. So all these nodes represent end of a successful search when the element to be searched is same as that particular node's value. For example, if X is A4, then you are going to follow this execution path and you're going to stop here and you are going to do 4 iterations of this loop. First iteration, second iteration, third iteration, 4 iteration. If your X is same as A9, then you are going to begin from here, you are going to come this side, and then you are going to come this side and you are going to compare X with A9 and you're going to stop here. So you're going to do 3 iterations. So if we are searching for an element which is at this level or root of this tree, which means if you're searching for A7, then we need 1 iteration of this binary search loop. And if we're searching for A3 or A11, then we need 2 iterations of this loop that we have written here. And if we're searching for A1, A5, A9, and A13, then we need 3 iterations. And if we're searching for any of the remaining elements, leaf elements, then we need 4 iterations of this loop. In general, the maximum number of iterations is equal to height of this tree that we've drawn. Height of this tree here means the number of nodes on the longest path. For this tree, the height is 4, right? 1, 2, 3, 4. So we need 4 iterations of this loop when we have an array of size 16 in the worst case. And worst case happens when you're searching for any of these elements, and we are talking about only successful search here, right? Not unsuccessful search. So for 16, we have height 4. What will be the height for any number when you have number of elements in the array from 17 to 32? Your height will be 5. If you have 17 elements, then you will have height 5 in this tree. If you have 18 elements, then again 5. Till 32, you will have the height 5. and from 33 to 64 you will have the height phi as 6, right? So height of this binary tree is ceiling of log n. If you have n elements in the array, it's going to be ceiling of log n. Here n was a power of 2, it was 16, so we had 4 height. If we have 17, then we are going to have 5 height. So height of this tree is log n, order of log n, and we are going to do maximum height iterations. So that's how we can say time complexity of binary search for a successful search is big O of log n. Let's now talk about unsuccessful search. Searching for elements which are not present in the array. How much time an unsuccessful search takes. Let's say we are searching for an element which is smaller than A0. Right? Say the smallest element in your array is 10 and you are searching for 5. So you will begin your search from the mid, A7, you will realize it is smaller than A7, you will come to A3. It's smaller than A3, you will come to A1. It's smaller than A1, you will come to A0. Right? Since it is smaller than A0, it's going to be smaller than these 3 elements and you are going to anyways come to here. And when you come to here, your low is going to be 0 and your high is also going to be 0. So we are going to compute the mid as a first thing and mid is turning out to be 0. So what are we going to do? We are going to compare mid element, which is A0 itself, with X, and A0 is greater than X. So if A0 is greater than X, if mid is greater than X, what are we going to do? We are going to change high equal to mid minus 1, which is 0 minus 1. So we are going to make high equal to minus 1, right? At this point, we will make our high as 0 minus 1. And we make high equal to 0 minus 1, low remains 0. So we do not enter into the loop next time. So we do again 4 iterations of this loop only, right? When we do not have this element in the array and when the element is smaller than A0. So we'll do 4 iterations of this loop when X is smaller than A0. What about the elements which are greater than A0 and smaller than A1? We'll follow this path. We'll come here because smaller than A1. Then we'll come here and then we'll go to the right side. When we go to the right side, we'll change the low and then low will become greater than high, right? So at this point, this is where all our unsuccessful searches will end, which are greater than A0 and smaller than A1. Similarly, here we'll have all our unsuccessful searches ending, which are greater than A1 and smaller than A2. And on the right side of it, greater than A2 and smaller than A3. Right? Similarly, all the leaves here will have those corresponding unsuccessful searches. Right? So in the unsuccessful search case also, we are going to begin the same path. We are going to compare array mid with X. It's not going to compare with the element is not present. Then we are going to either fall into this case or this case. Whatever case we are falling in, we are always going to end up with a situation where low becomes greater than high or high becomes smaller than low. Both are same things. So if that happens, we are going to come out of this loop, right? So we are still going to do big O of log n iterations of this loop, even if the element to be searched is not present in the array. So we have been saying that we do big O of log n iterations of this loop. Now how much work we do in every iteration? We do some constant amount of work. All these computations are constant computations. So that is how our time complexity is big O of log n. And in case of unsuccessful searches, it's always going to be log n. So for unsuccessful searches, we can say it's theta log n. But in case of successful searches, we can say it's big O of log n. It can be any number of iterations beginning from 1 to log n.